Hello everyone, my name is Zhenxuan, and today I'll be presenting my research on Q-switch pulse generation in an erbium doped fiber laser using a bis 8 hydroxyquinoline natto 110 phenanthrene magnesium 2 complex thin film saturable absorber. Before I begin my introduction, I will briefly explain some of the key terms that will be mentioned throughout the presentation. First of all, Q-switching is a laser technique used to generate short, energetic pulses by alternating the intracavity loss or the quality factor of the laser system. Next, a saturable absorber, or SA for short, is a photonic material whose absorption decreases as incident light intensity increases. SA's nonlinear property enables passive Q switching or passive mode locking, as it can act as a self-switching shutter. Lastly, the C-band is a radio frequency spectrum ranging from 1530 to 1565 nanometers and is primarily used in optical communications due to its balance between high-speed data capacity and wide coverage. Now, moving on to the introduction, among many pulse lasers, the application of Q-switch fiber lasers is significant and has been applied in various areas such as optical communication, environmental sensing, biomedical diagnostics, and precision microprocessing. Q-switching can be achieved either actively or passively. Active Q-switching requires external modulation like an acousto-optic modulator, which comes with significant drawbacks, namely high cost and system complexity, while passive Q-switching typically relies on saturable absorbers, making the system simpler and more cost-effective. However, one key challenge in this field is the limited availability of efficient and stable saturable absorber materials, especially in the C-band region around 1550 nanometers. Existing materials such as graphene, carbon nanotubes, and semiconductor saturable absorber mirrors each have limitations, either high fabrication costs, complex integration, or limited stability. Therefore, there is a clear need for alternative saturable absorbers. Organic metal chelates are known for their structural stability, thermal robustness, and strong optical properties, an example of which, aluminum Q3, has already demonstrated success as a saturable absorber. Bis 8 hydroxyquinoline natto 110 phenanthrene magnesium 2 complex, or magnesium FeNQ for short, is an organic metal chelate that belongs to a class of compounds known as metal quinolinate. And in this study, I have explored its potential as a new saturable absorber for Q-switching. The magnesium FeNQ was incorporated into a PVA matrix to form a thin film using the solution casting method. The film was then integrated into an erbium doped fiber laser cavity using a ferrule to ferrule sandwich structure, where the thin film is placed between two fiber ferrule connectors using optical gel. Through this method, a direct interaction is established between the propagating light and the saturable absorber. Now I will briefly explain what an erbium doped fiber laser, or an EDFL, is. An EDFL is an example of fiber laser that uses optical fiber doped with erbium ions as the gain medium. When the cavity is pumped with light at 980 or 1480 nanometers, the erbium ions are excited to a higher energy level, and as they relax, they emit photons around 1550 nanometers, which are then amplified through optical feedback in the fiber cavity to produce laser output. Here is a diagram of the EDFL cavity configuration in my study. The system begins with a 980 nanometer laser diode, which provides the pump energy that excites the erbium ions. This pump light is combined with the signal wavelength using a wavelength division multiplexer, or WDM. The combined signal then enters the erbium doped fiber, where amplification occurs. An isolator ensures that propagation of light is unidirectional, preventing unwanted reflections. 9010 cover extracts 10% of the light for characterization while maintaining the feedback in the cavity. The magnesium FeNQ saturable absorber is then introduced into the cavity to enable passive Q switching. Finally, to analyze the performance of the magnesium FeNQ thin film saturable absorber, 3 diagnostic tools were used. An oscilloscope was used to observe the pulse train. An optical spectrum analyzer measured the wavelength distribution of the laser output, and a radio frequency spectrum analyzer was used to evaluate the stability of the pulses by analyzing the output power at different frequencies. Now, moving on into the results and discussions. Without the saturable observer, the laser operates at a continuous wave mode. However, after inserting magnesium FanQ thin film saturable observer, stable passive Q switching was observed. This confirms that magnesium FanQ film provides necessary nonlinear loss modulation required to initiate and sustain passive Q switching in the EDFL. Looking at the pulse characteristics, stable periodic pulses were observed over a pump power range from approximately 129.67 to 180.44 milliwatts. The pulse-to-pulse interval was about 28.8 microseconds, and the pulse duration was measured at 9.38 microseconds. This demonstrates consistent and stable pulse generation. From the optical spectrum analysis, the laser output was centered at around 1557.4 nanometers, with a spectral bandwidth of approximately 2.2 nanometers. This confirms that the system operates within the C-band and maintains a stable emission at the dedicated wavelength. The RF spectrum further verifies its stability. A distinct fundamental frequency peak at 70.93 kHz was observed, with a signal-to-noise ratio of about 44.86 decibel. A high SNR combined with low noise floor indicates a high temporal stability and a consistent pulse generation. Now looking at how the system responds to the increasing pump power. As the pump power increases, the repetition rate increases while the pulse width decreases. This is because higher pump power leads to higher gain, allowing the system to reach the threshold for Q-switch pulse generation more quickly. As a result, pulses are generated more frequently and become shorter in duration. In terms of energy and peak power, they both increase with pump power. Pulse energy increased from 6.74 picojoules to 12.6 picojoule, while peak power increased from 0.405 milliwatts to 1.345 milliwatts. However, at higher pump power, the growth becomes less pronounced. This indicates that the saturable observer had begun to approach its bleaching limit and was unable to further increase its modulation depth effectively. Finally, examining efficiency, the output power increases with pump power linearly, reaching a maximum average output of about 0.46 milliwatts. The slope efficiency is approximately 0.57%, which is relatively low. This suggests that while the system with magnesium FanQ as saturable observer is stable, it experiences high cavity loss, high thermal load, and low output power. In conclusion, bis-8 hydroxyquinolinato 1,10-phenanthroline magnesium 2 is a promising thin film saturable observer for the realization of compact pulse EDFL sources operating in the C-band region. The material shows excellent stability and moderately high signal-to-noise performance, making it a viable candidate for a compact Q-switch pulse fiber laser system. However, its main limitation is low efficiency, resulting in low pulse energy compared to some of the existing materials. In this study, stable passive Q switching has been successfully demonstrated at 1557.4 nanometers using a magnesium FanQ thin film saturable observer. In terms of significance, this work contributes to the development of an alternative saturable observer material. Such systems could be useful in medical applications that require short, high-intensity pulses with minimal thermal damage, such as tattoo removal, ophthalmology, and lithotripsy. In the future, explorations on other metal complexes with similar ligand structures could be conducted to determine alternatives with higher efficiency. A comparative study with established materials will also help better position magnesium FanQ within the field. Thank you for your attention, and I welcome any questions. Here is my works cited.